Welcome to Climate DIY Dynamics. Today we're going to be modeling a gnarly weather phenomenon, an atmospheric river, and I'll be explaining the science behind these vessels for intense precipitation events. The coolest part? We'll be using equipment that you might be able to find in your own home or at a nearby store. So let's just start off by asking, why do we care about atmospheric rivers? Well, atmospheric rivers are important because they can be a vital source of water for regions in the subtropics, like the western US, Canada, Australia, and more, accounting for more than half of the annual rainfall in some places. But since the storms these rivers produce are so large and happen so fast, they also come with a substantial risk of floods, mudslides, and other hazardous disasters. Now that we know what we're dealing with, let's jump into the experiment. So here we've got a record player. Any old record player will do as long as you're working on a level surface. Now, on the record player, we're going to put this cylindrical tank. Now, this tank was custom built to fit on this record player, and we bored a hole in the bottom so it will sit nice and centered on that needle. But any tank of similar size should work. Lastly, we just need a couple more things. Small metal can, a paint can or tomato can should do, some ice, and 2 different color food dyes.
So now that we have all that, let's get started. You'll see I filled up the tank with water. I was shooting for about 4 to 5 centimeters of depth or so, and it looks like I have that. Next, we're going to grab our tomato can or paint can or whatever's on hand, and we're going to fill it with ice, then compact the ice as much as possible, and then add cold water until the can is full.
This next part requires a keen eye and steady hand. We're going to place the can of ice directly in the middle of our tank. Then after that, we let a record player spin for at least 5 minutes. The slowest this one spins is roughly 16 RPM, which is still a little fast, but we can still use it for our model. We need to let it spin up so that all of the fluid is moving together, unperturbed, at the same speed as the tank.
While we wait, let's go over our planetary system model that we've just built together. So this tank represents a rotating planet. The water in the tank is our atmosphere, and the ice in the center represents the geographic pole. And we know that on Earth, it's very cold the closer you get to the poles, and it gets warmer the closer you get to the equator, which is represented here by the edge of the tank. So it's sort of like you're looking down on the Earth from the North Pole. Now the change in temperature is what we call a meridional temperature gradient. This just means that there's a difference in temperature from north to south along the meridians, which are these longitudinal lines that run along the globe.
Alright, our tank has been spinning up for long enough now, so we can get to it. Now, I've used some movie magic to derotate this video so it's easier for our eyes to follow, but the tank is still spinning. Now, we add in some blue food dye close to the can of ice. What this does is it allows us to see the movement of water in our model, which represents, or is a proxy for, air near the North Pole. As our planet rotates, the cold air starts to move towards the outer edge of the tank. This is the same thing that happens on Earth. Cold air is dense, and so gravity will pull it down, and the air will disperse away from the poles and into the mid-latitudes. But since our system is rotating, there are Coriolis forces present, and in a frame that is rotating counterclockwise, Coriolis forces will deflect fluid motions off to their right. So what we see as our planet spins some more is that the cold air isn't just moving outward, but it's moving into these spiraling patterns. The fluid is becoming what we call baroclinically unstable. In our atmosphere, these large instabilities, or eddies, can cause huge winter storm events, and we see similar structures in our record player experiments. Now, what's happening with the warmer air, or the water towards the edge of our rotating tank? Well, I'll show you. Next, we're going to add in some green food dye on the outside of one of these eddies to highlight the warm fluid. It'll take a second, but after I drop the green food dye in, you'll see that the warm air starts to fill in everywhere that the cold air isn't. And if we wait, we'll observe that the warm air stretches out along the front of the spiraling eddy and is compressed, or bulldozed by the eddy, into a tight green stream of dye. This green stream in our desktop experiment represents warm air, and it is our analog to an atmospheric river. So we have this green fluid that's supposed to represent a big mass of water vapor in the sky, but you don't really have a sense of what that's supposed to look like and how our model captures it. But if we take the satellite image from NASA's Goddard Earth Observing System of an atmospheric river that hit the coast of California in January 2023, now we see just how effectively we can build a physical model of this real-world phenomenon. Now that you have a better understanding of the model, I want to go back and have you watch it again really fast, this time with our satellite image right next to it. Based on what you've learned so far, see if you can get a sense for how the motion of the fluid causes our desktop atmospheric river to form.
Now, a characteristic of air in the tropics, or the region around the equator, is that it's very warm and very moist. It contains a lot of water vapor. So when an air current picks up this dense, moist pocket of warm air, it flows like a river through this BCI event like we just saw. And they can flow for hundreds and hundreds of miles. Eventually, like we observed, the river hits a wall, the wall being a pack of cold air. And when a huge pocket of warm air with water in the vapor phase suddenly hits a huge pocket of cold air, what do you think happens? Well, let's think. If water in the liquid phase gets really, really hot, it evaporates into water vapor, right? So if water in the vapor phase gets really cold, that's right, it goes back into the liquid phase. The water in the vapor phase condenses very quickly, so you have an unbelievable amount of water that was just a gas suddenly condensing into a liquid all at once. This can cause several inches of precipitation over a large region in very little time. Now, this experiment shows that it's very easy to end up with the conditions needed to form atmospheric rivers, as long as you have a temperature gradient, fluid, and rotation. In fact, across several experiments in our lab, whether we were trying to show them or not, we end up with these desktop models of atmospheric rivers. We can spin the tank at a different speed, within reason, of course. Increase or decrease the amount of water, change the size of the tank, and we still see the same results. So, what does that imply for the formation in Earth's atmosphere, as climate conditions vary over time? Well, due to global warming, scientists expect to see an increase in the intensity and the frequency of atmospheric river events. So it's important that we as scientists monitor atmospheric rivers so that we can help plan on how to manage water supply or prepare for floods. This has been Atmospheric Rivers with DIY Namics. I hope you learned something today, and I hope to see you next time.